At the edge of a black hole, time slows, light bends, and the laws of physics begin to break. But what lies beyond that invisible boundary? Tonight, we'll journey into the heart of the universe's darkest mystery. If you enjoy cosmic explorations, please like, subscribe, and share, and tell us in the comments, what do you think truly waits inside a black hole? Thank you for watching. Now let's begin. Around the black hole, the galaxy stretches in every direction as a soft haze of starlight and dust. The structure of the Milky Way arches like a shallow spiral, each arm filled with stars in quiet orbit clouds of hydrogen and drifting lanes of molecular gas. Somewhere within this immense rotation lies the dark gravitational anchor at the galaxy's core, a region where countless paths of matter have bent for millions of years toward the same invisible center. The background remains tranquil from a distance, a slow movement that takes millions of years to alter its shape. Stars pass one another in silence, their faint light spreading through the interstellar medium absorbed and re-emitted by thin dust. The scale is almost motionless to human sense, yet gravity is active everywhere, forming the delicate architecture that holds the galactic plane together. Over vast time, clouds condense under this influence, forming new stars while others collapse and die. The balance is maintained by the total mass of the galaxy, but near the center, that balance begins to tilt. The dark mass at the heart of the Milky Way, known as Sagittarius, a star, exerts its influence over tens of light years, guiding the motion of stars in precise elliptical orbits. Each orbit is an expression of invisible curvature, space itself bent by gravity into paths that never straighten. The stars closest to the center, observed over decades, move with astonishing speed, thousands of kilometers per second, yet they remain in stable motion, evidence of something immense and compact hidden within. Around them, diffuse gas flows inward from the surrounding galactic bulge. The bulge is a dense region filled with older stars, supernova remnants, and traces of magnetic fields threading the plasma between them. The temperature rises gradually toward the center, not because of proximity to heat, but because the gas encounters denser regions and begins to compress. Tiny collisions among particles add energy, converting slow drift into directed fall. The black hole itself emits no light, but its environment becomes luminous through friction, radiation, and magnetic activity. From afar, telescopes observe a faint glow at radio wavelengths, scattered across light years of surrounding material. This is the feeding ground from which the black hole draws its energy. The gas here does not fall directly inward. It moves within a vast turbulent reservoir where competing forces of gravity, pressure, and magnetic tension shape its slow descent. Clouds of ionized hydrogen drift closer, their atoms torn apart by ultraviolet light and high-energy collisions. As density increases, the medium changes from transparent to opaque, forming pockets of warmer plasma that flicker faintly. At this outer edge, the boundary between the galactic environment and the accretion region begins to form. The black hole's influence extends through subtle acceleration. Every particle that crosses a certain distance becomes trapped in its gravitational well, even if escape is still theoretically possible. Over time, angular momentum keeps matter from plunging straight inward, forcing it to spiral slowly like a widening current around a drain that cannot yet be seen. The scene remains dominated by balance rather than violence. The black hole does not reach outward to take. Instead, gravity quietly persuades everything nearby to follow the simplest path through curved spacetime, a path that leads inward. On the scale of centuries or millennia, streams of gas reorganize into thin flows, tracing invisible channels through magnetic fields. These fields, anchored to the moving plasma, stretch and twist, storing energy, that will later shape the accretion disk. Even at this great distance, the effect of the central mass can be inferred. Stars orbit faster as they approach the center, following the predictions of general relativity with remarkable precision. The orbits are not disturbed by collisions or interactions. They move cleanly in curved space, revealing the black hole's mass by their steady dance. Around this gravitational focus, time itself behaves differently. Clocks placed closer to the center would tick more slowly compared to those far away, an effect of time dilation that begins long before the event horizon is reached. Yet for now, the difference is small, measurable only through precise observation. The galaxy continues its calm rotation, unaware of the slow inward drift occurring at its heart. From the outskirts of the Milky Way, the center appears as a dim glow in the direction of Sagittarius, partially veiled by interstellar dust. Infrared and radio telescopes pierce this obscuration, revealing a dense region about 30,000 light-years away. Within that small patch of sky lies a mass equivalent to 4 million suns, compressed into a volume smaller than the orbit of Mercury. The surrounding space is neither empty nor still. It is a slow storm of charged particles guided by invisible curvature heating as they descend. Each particle's fall marks a conversion of potential energy into light radiation and magnetic activity. The process is inefficient compared to the energy stored in matter, yet over cosmic time it shapes the luminous core of the galaxy. The galactic center is not a place of sudden events, but of enduring interactions. Every stream of gas, every fragment of dust is part of a steady inflow that began in the wider galactic arms. The path toward the black hole begins in quiet surroundings where gravity barely whispers. Step by step it grows stronger, curving space more sharply and altering the behavior of matter with increasing authority. In this region, light still travels freely, stars still orbit safely, and the black hole remains unseen. Its presence is known only through motion, the swift turn of nearby stars, the faint radio hum of warm gas, and the way space itself seems to tighten as one looks inward. Here at the outermost layer of influence, the journey begins not with collapse or violence, but with stillness. The black hole rests at the quiet center of its domain, patient, motionless, shaping the dance of the galaxy through the silent pull of gravity. All motion leads inward, slowly, inevitably, across distances that defy comprehension. Even far from the black hole itself, gravity begins to alter the landscape of motion. Every orbit in the galaxy's core bends slightly inward, guided by a curvature too subtle to see, but powerful enough to rule the region. The effect is not confined to nearby stars. It extends across light years, shaping the orbits of clusters and streams of gas as they trace elliptical paths around the central mass. The gravitational field of the black hole is not a simple pull in the ordinary sense. It is the geometry of space itself being reshaped. Objects do not fall toward a force. They move along the most natural curves of spacetime curves that bend more sharply closer to the center. This invisible structure defines the choreography of matter, turning random motion into ordered rotation, creating equilibrium between infall and centrifugal escape. The distant region remains stable, a slow swirl where orbits last for thousands of years. Yet the influence of the black hole is already measurable. Astronomers record the motions of individual stars that approach the central point and accelerate dramatically before sweeping outward again. Their predictable returns reveal the immense, compact nature of the object they circle. The geometry that governs them is continuous, smooth, and silent. In the emptiness between stars, gravity acts through space-time curvature, not through physical contact. Light from these stars also follows the bent geometry. As it passes near the core, its path curves slightly, a phenomenon known as gravitational lensing. To distant observers, background stars appear displaced as if the region itself distorts sight. This bending of light offers the first visible trace of the black hole's reach. The distortion is mild here, only enough to reveal curvature, but it will grow as one moves closer. At this distance, the black hole's presence resembles a lens set within the galaxy's heart, magnifying and warping whatever lies behind it. The energy field that defines this curvature extends infinitely but weakens with distance. The measure of its strength can be imagined as the rate at which space bends per unit of mass. For a supermassive black hole, the bending remains gentle even at great scales, yet its cumulative effect dominates the galactic center. The outer stars continue their long circuits undisturbed, but within a few light years motion begins to quicken. The balance between ordered orbits and random turbulence tilts toward collapse. Gravity quietly organizes chaos, turning diffuse matter into structures that spiral inward. In these intermediate zones, collisions among gas particles become more frequent. Each interaction converts motion into heat, and as heat rises, the gas emits faint infrared radiation. Observers detect this glow as a trace of the invisible descent. The inflow of matter is not steady. It occurs in episodes shaped by the distribution of gas clouds in the galactic core. A supernova in a nearby region may push a wave of gas toward the center, where it gradually falls under the black hole's control. Over centuries, such flows sustain the slow growth of the central mass. Nothing here moves quickly by human measure. The distances are too vast and the energy required to change direction too great. The galaxy's core functions as a vast reservoir with gravity as the organizing principle. Each particle of dust, each atom of hydrogen feels the same pull. In the calm environment of the outer bulge, this pull is imperceptible, but it defines the architecture of the future accretion disk. Even magnetic fields stretching across light years begin to align subtly with the direction of gravitational flow. They trace invisible channels through which charged particles will later spiral. The interaction between magnetic lines and gravity creates a complex web of motion not easily visualized, but quietly shaping the flow of plasma long before the accretion disk forms. Beyond this region, gravity also affects the trajectory of photons emitted by surrounding stars. Their paths bend slightly toward the central mass, their travel times lengthened by the curved geometry. These effects, though tiny, reveal the nature of general relativity at work. Space and time are not fixed backgrounds here. They respond to the mass embedded within them. The more mass accumulates, the deeper the curvature becomes, creating a gradient in the flow of time itself. Near the galactic periphery, time proceeds normally by our standards. Closer in seconds stretch imperceptibly. This dilation grows stronger as the journey moves inward. To an external observer, it would seem as if everything near the black hole runs a little slower, every rotation delayed, every pulse of light slightly redshifted. Yet for those local to the region, motion and time feel unchanged. It is the distant universe that seems to move too fast. This relativity of perspective defines much of the black hole's domain. There is no sudden boundary where gravity begins. It is continuous deepening smoothly with proximity. The galactic core thus becomes a quiet gradient from the familiar to the extreme, from the steady orbits of stars to the curved paths of light itself. The journey toward the black hole passes through this invisible field, where geometry replaces force and motion becomes an expression of shape. In the vast silence of the galactic center, the dominance of gravity is complete, but calm. Every path curves gently inward, every photon bends slightly, and every orbit whispers the same direction toward the heart of the void. Within a few light years of the black hole, the surrounding space fills with the thin, turbulent medium of gas and dust. This is the inflow reservoir, the slow feeder of the immense gravitational engine at the centre. It is neither uniform nor calm. Pockets of denser material drift within a broader sea of ionized plasma, colliding, fragmenting and heating as they interact with one another. The gas originates from dying stars' stellar winds and remnants of ancient supernovae that have enriched the galactic core with heavy elements. Each particle, each atom has been released from a distant source and now drifts through the deep gravitational gradient that leads toward the unseen center. The density remains low, far lower than the best vacuum achieved in laboratories on Earth, yet over cosmic distances the total mass is significant. The particles here move erratically, driven by random turbulence and weak magnetic fields that twist through the medium. Occasionally a shock wave from a nearby stellar explosion compresses the gas, triggering temporary flares of light as atoms recombine or become ionized once again. The temperature of this vast cloud varies with distance. Farther out, it remains cool only a few hundred degrees above absolute zero. Closer in, collisions raise the heat, and the radiation from the inner regions begins to ionize the gas-stripping electrons from atoms and creating a plasma that glows faintly in infrared and radio wavelengths. Observations at these frequencies show a mottled, flickering structure, evidence of turbulence and variable density. The reservoir behaves as both source and barrier, feeding the black hole slowly while dissipating much of its energy as light and heat. Gravity draws the gas inward, but angular momentum resists collapse. Each particle carries a small component of rotation inherited from the galactic motion of its parent system. This rotation prevents a direct fall, forcing the gas into spiral paths that gradually tighten over time. In this region, the balance between inward pull and sideways motion begins to define the shape of the accretion flow that will later form. The gravitational potential deepens toward the center, converting random drift into directed descent. The conversion is not instantaneous. It unfolds over thousands of years. The magnetic fields frozen into the plasma create filaments and loops that resist compression, generating patterns of circulation that resemble eddies in a slow whirlpool. Over long intervals, these magnetic structures reconnect and break, releasing bursts of energy that briefly illuminate the darkness. The interplay between magnetism and gravity dominates the dynamics here, stirring the gas and heating it through friction and electrical currents. The plasma becomes an intricate mixture of motion and heat, a living turbulence that feeds the central engine without yet revealing it. Radiation escapes freely at this stage, carrying away much of the thermal energy generated by collisions. This cooling allows new inflows to continue, preventing immediate stagnation. Over time, as matter loses angular momentum through collisions and magnetic interactions, it sinks inward. The orbits flatten into a roughly equatorial pattern, forming the earliest stages of an accretion structure. There is no single boundary marking where the reservoir ends and the disk begins. It is a gradual transition, a slow condensation of motion into order. At its outer edges, dust grains still survive, heated but not yet destroyed. As they move closer, they evaporate their atoms, joining the plasma. Molecules of carbon and oxygen that once formed part of interstellar clouds are torn apart by radiation and collisions. Chemical complexity gives way to simplicity, and the medium becomes fully ionized. It now responds to magnetic fields as much as to gravity. Spiral filaments of plasma drift toward the midplane where density and temperature rise. The light they emit shifts from infrared to visible, and finally to X-ray, as the energy of collisions increases. These emissions are intermittent, changing on timescales of hours or days, revealing the dynamic nature of the inflow. From a distance, telescopes record these fluctuations as flickering brightness around the galactic core. Each variation corresponds to shifts in density or magnetic activity within the reservoir. It is through such changes that the black hole's feeding process becomes visible. The physics here is governed by the transfer of angular momentum. For matter to fall inward, it must shed part of its rotational energy. Magnetic fields act as the agents of this exchange, coupling different layers of the plasma so that inner regions slow while outer regions accelerate slightly. This redistribution allows material to drift closer to the center while maintaining overall conservation of motion. The process is inefficient but steady. It transforms random chaos into organized rotation, shaping the base of the luminous disk that will soon dominate the view. The gas that lingers in the outer regions forms a halo around the accretion flow, heated to millions of degrees and emitting X-rays detectable from Earth. These high-energy photons mark the boundary between the inflow reservoir and the active disk. The halo remains turbulent, a buffer between the galactic medium and the region of strong gravity. Here matter can still escape. Some particles gain enough energy from collisions to break free entirely, joining the interstellar winds that flow back into the galaxy. Yet the majority continue inward, losing energy and momentum through countless small interactions. The inward motion accelerates subtly, and temperature rises until the radiation from the gas becomes self-sustaining. Photons scatter repeatedly, trapped by the density of the plasma, contributing to further heating and compression. In this way, the inflow reservoir serves as a slow funnel, transforming diffuse interstellar matter into a concentrated rotating storm of plasma. Nothing abrupt marks the transition. The change is continuous, measured only by increasing density, heat, and order. Gravity orchestrates this progression without noise or suddenness, shaping the environment into concentric zones of rising energy and narrowing motion. From the perspective of the galaxy at large, this process is invisible, masked by the brilliance of nearby stars. Only at certain wavelengths can its presence be discerned, but within the calm darkness, the transformation proceeds relentlessly, converting random cosmic debris into the structured motion that will soon define the luminous heart of the accretion disk. It is here in this quiet but dynamic layer that the black hole begins to reveal its influence, not through destruction, but through the slow, patient organization of matter, guiding it inward, one orbit at a time. As matter drifts inward from the reservoir, its rotation becomes organized into a vast flattened disk encircling the black hole. This is the birth of the accretion flow, a region where gravity friction and magnetic turbulence interact to convert potential energy into heat and radiation. The formation is gradual, the product of countless collisions and magnetic exchanges that align the angular momentum of individual particles into a single coherent motion. From afar, the disk appears as a luminous whirl, though no solid surface defines it. Every point within it is fluid plasma bound by the geometry of spacetime and the unrelenting draw of gravity. Near its outer edges, the gas remains relatively cool, its temperature measured in thousands of degrees. But closer to the center, the frictional interactions between neighboring layers intensify. Particles in adjacent orbits move at slightly different speeds, and their collisions transfer energy, heating the medium until it glows across the electromagnetic spectrum. The gradual inward spiral of matter generates the very light by which the black hole is observed. The conversion efficiency of this process is extraordinary. A small fraction of the infalling mass can radiate more energy than entire stars over their lifetimes, yet this brilliance emerges from processes that occur in complete silence. The disk is thin compared to its diameter, a ribbon of plasma only a few % as tall as it is wide. Its shape is maintained by the balance between thermal pressure, pushing outward, and gravity pulling inward. Above and below it, tenuous coronal plasma extends threaded with magnetic loops that rise and fall as they reconnect. These magnetic fields are crucial. Without them, the disk could not effectively transfer angular momentum, and matter would remain in stable orbit indefinitely. The magnetic turbulence acts as a conveyor of motion linking distant regions, so that energy flows outward while matter drifts inward. This mechanism, called magnetorotational instability, stirs the disk into a constant low-frequency chaos that redistributes momentum and maintains the inflow. The turbulence is neither random nor entirely ordered. It follows patterns shaped by field lines and orbital shear, forming vortices and filaments that stretch around the disk. Occasionally, localized heating creates temporary bright spots areas where friction or reconnection has momentarily increased radiation. These regions orbit the black hole at high velocity, creating fluctuations in brightness, detectable by telescopes observing at radio and X-ray wavelengths. Such variations measured over hours or days provide one of the few means of probing the dynamic structure near the event horizon. The motion within the disk is extraordinarily fast. Closer to the center, orbital periods shorten to minutes, and the flow approaches a significant fraction of the speed of light. Yet even at these velocities, the structure remains coherent each layer, following the curved geometry of spacetime. In general relativity, orbits near a black hole deviate from the familiar Newtonian ellipses. They precess continuously, and circular stability is lost near the inner regions. The disk, however, maintains equilibrium through the continuous exchange of energy and momentum. The light it emits escapes in complex paths bent and delayed by the gravitational field. To a distant observer, the disk appears warped, with the far side partially visible through light that has been curved around the black hole. This distortion reveals the depth of the gravitational well without ever exposing the object itself. The inner edge of the disk approaches the limit known as the innermost stable circular orbit, beyond which material can no longer remain in steady motion. As matter crosses this boundary, it plunges inward rapidly, completing its spiral in milliseconds. Before that final descent, however, it radiates the last of its energy, producing the most intense light in the system. This inner region is the primary source of the black hole's brilliance, its luminosity fed by friction and magnetic tension. Above the disk, thin funnels of magnetic field begin to twist into alignment with the rotation axis. These structures, invisible except through their effect on charged particles, will later become channels through which energy escapes in the form of narrow jets. For now, they serve as scaffolds within which plasma flows rising and falling in rhythmic loops. The entire structure is dynamic but balanced, a sustained storm of matter, converting motion into heat and light. From a distance, the disk resembles a steady glow, but within it lies perpetual turbulence, billions of collisions per second, and a complex dance of magnetized plasma. Radiation pressure acts outward, opposing gravity, and in some regions the balance oscillates, creating waves that ripple through the disk like soundless tides. The total luminosity depends on how much matter the black hole consumes. When the inflow rate increases, the disk brightens dramatically. When it declines, the light fades. These cycles can last years or centuries depending on the available fuel. The light that escapes carries information about temperature, density, and velocity encoded in its spectrum. High-energy X-rays originate from the innermost orbits while visible, and ultraviolet light arise farther out. Each wavelength maps a different radius, allowing scientists to reconstruct the structure indirectly. Despite the violent energies involved, the process is remarkably stable. The disk endures, maintained by the balance of forces acting across every orbit. Its color, shape, and brightness reveal the black hole's mass, and spin though the object itself remains hidden beyond the reach of light. At this stage of the journey, the environment becomes overwhelmingly bright, but still comprehensible through physics that can be observed and tested. It is the last region where matter behaves in familiar ways, following equations that describe fluid motion and electromagnetic interaction. Closer in, the gravitational field strengthens so rapidly that even these equations begin to strain under the curvature. For now, the accretion flow remains the dominant feature, a structure of organized chaos sustained by gravity's precision. The black hole feeds quietly, transforming random cosmic matter into pure radiation. Its power is immense, but governed by balance, a luminous stillness surrounding an unseen core. The accretion flow is both a veil and a revelation, a layer where light is born from falling matter, tracing the invisible contours of space-time on its way toward the event horizon. Deeper inside, the accretion disk transforms into a realm of extreme conditions, where matter moves close to the speed of light, and temperatures reach tens of millions of degrees. The structure remains thin but grows denser, its radiation pressure rising until it nearly counterbalances the weight of the infalling gas. In this environment, particles no longer follow simple orbits. Each atom of plasma traces a spiral path dictated by the curved geometry of space-time and the intense differential rotation around the black hole. The friction between layers converts orbital energy into heat so effectively that the gas emits radiation across nearly every wavelength, from infrared to ultraviolet to powerful X-rays. The inner disk is not static. It seethes with motion, turbulent yet orderly enough to sustain itself for eons. The photons released here encounter gravity so strong that their paths are bent immediately. Some escape outward, curving around the black hole before reaching distant space, while others are redirected back into the disk, contributing to further heating. Light that does escape carries information about the velocity and temperature of its origin, redshifted by the stretching of space-time as it climbs out of the gravitational well. This redshift softens even the most energetic radiation, transforming intense X-rays near the core into weaker emissions by the time they arrive at distant detectors. To an observer, the region appears bright yet strangely dimmed, as though viewed through a veil woven from gravity itself. The balance of forces here is delicate. Magnetic fields generated by the rotating plasma rise and collapse in endless cycles, twisting around themselves and reconnecting in flashes that release sudden bursts of energy. These reconnection events create transient hot zones that orbit rapidly, producing variations in brightness measurable across minutes or hours. Observations of these fluctuations allow scientists to map the disk's rotation and infer the spin of the black hole. Closer still, the geometry of space-time dominates all motion. The velocity gradient between adjacent layers becomes immense, producing shear that amplifies turbulence. Friction and magnetic tension drive a steady inward drift, each parcel of plasma losing energy as it moves closer to the center. The radiation pressure is intense enough to alter the disk's structure. In certain regions, the outward push of light nearly equals the inward pull of gravity, creating a quasi-stable layer where inflow slows before resuming. These zones, known as radiation-supported regions, represent the final stages of the disk before the plunge begins. The light emitted here contributes most of the black hole's luminosity, forming the glowing ring observed by telescopes like the Event Horizon Telescope. At these radii, time dilation becomes significant. For a distant observer, processes here appear to slow down. flashes of light linger and orbits seem stretched in duration. Yet for the matter itself, time flows normally. The plasma completes thousands of rotations before it loses enough angular momentum to fall inward. Each orbit tightens imperceptibly, the spiral drawing ever closer to the point of no return. Above the disk, the corona of hot electrons grows active, scattering photons into higher energies through inverse Compton interactions. This coronal emission produces the variable X-ray glow that often accompanies accreting black holes. The corona's structure is sustained by magnetic fields rising from the disk and twisting into loops that extend thousands of kilometers above its surface. When these fields reconnect, they release flares that briefly outshine the underlying disk. The interaction between the disk and its corona establishes a feedback cycle. Radiation from the disk heats the corona, while the corona's high-energy photons penetrate the disk, heating it further. This interplay maintains the luminous equilibrium of the inner region. Meanwhile, general relativity governs every detail of motion. The curvature of spacetime near the black hole causes orbital precession. Each loop of plasma shifts slightly, never closing perfectly. Over time, these shifts smear out local irregularities, maintaining the disk's symmetry. The gravitational redshift also affects photons differently depending on their direction. Light emitted toward the observer appears brighter and bluer because it originates from matter moving toward us, while light from the far side appears redder and dimmer as it recedes. This relativistic beaming effect gives the ring around the black hole its characteristic asymmetry, one side bright, the other subdued. The entire system appears distorted, yet it follows the precise predictions of Einstein's equations. Beneath this complexity lies quiet order. Despite turbulence, flares, and relativistic speeds, the disk sustains a continuous stable flow of matter. Each particle plays its role in transferring energy outward and mass inward. The luminous whirl it forms is not chaotic destruction, but steady transformation. The black hole itself remains silent, invisible, behind the glow defined not by emission but by absence. To reach this region is to approach the final frontier of observable physics. Within a few gravitational radii, the escape of light becomes uncertain. Some photons still climb outward, following curved paths that loop several times before escaping. Others hover temporarily trapped in orbit at the photon sphere before being drawn inward. The transition from emission to capture is gradual but exorable. Every step deeper carries less chance of return, yet there is no abrupt change in the physical experience of the plasma. The same equations describe it until the last stable orbit. Beyond that, motion accelerates irreversibly toward the horizon. The inner accretion disk thus represents the final domain where the universe still allows observation. All phenomena here, heat, motion, light, and magnetic structure, are visible or inferable. Inside the horizon, these vanish from view, replaced by silence. For now, the disk continues to shine, converting falling matter into radiant energy with unmatched efficiency. It is the visible manifestation of an otherwise hidden process, the transformation of gravitational potential into light. The closer one moves toward the center, the more extreme this transformation becomes, until even the concept of stable orbit fails. The inner disk ends not with a boundary, but with a transition, a thin invisible line where order gives way to free fall and all trajectories curve inward beyond recovery. It is here at this luminous edge that the black hole reveals both its greatest brilliance and its greatest concealment. At the inner edge of the accretion disk, magnetic fields dominate the behavior of plasma. These fields are not fixed lines threading through space, but dynamic structures generated by the motion of charged particles within the disk. As matter orbits at relativistic speed, the movement of ions and electrons amplifies weak seed fields into powerful magnetic frameworks. These lines twist and loop through the rotating gas, sometimes piercing the disk's surface, sometimes winding tightly around it. The result is an intricate magnetic landscape that channels energy from the disk toward the poles. Within this region, magnetism and gravity reach equilibrium, creating conditions where the flow of plasma is no longer governed purely by mass and temperature, but by electromagnetic tension. Above and below the disk, magnetic lines converge into two narrow funnels, aligned roughly with the black hole's rotation axis. Within these funnels, charged particles accelerate to nearly the speed of light, forming twin jets that extend for thousands of light years. Each jet carries energy away from the system, collimated by the very fields that generate it. The material within these jets is sparse but energetic, composed of electrons, positrons, and atomic nuclei stripped bare by the heat of the disk. As they stream outward, the particles spiral along the magnetic lines, emitting radiation through synchrotron processes that produce a continuous spectrum of radio and X-ray light. To distant observers, these jets mark the only visible extension of the black hole's influence beyond its immediate surroundings. The jet mechanism is complex, but can be understood as an exchange between rotation and magnetism. The spinning plasma drags magnetic field lines around, with it winding them like twisted cords. The tension within these cords builds until energy is released along the axis of rotation, accelerating particles outward. The process also extracts rotational energy from the black hole itself through the frame-dragging effect in which spacetime is pulled into motion by the black hole's spin. This coupling between magnetic fields and rotation forms one of the most efficient engines in nature. Despite their violence, the jets move through an environment that remains largely silent. Space provides no resistance, so the streams continue undisturbed for immense distances, sometimes escaping the galaxy entirely. They interact with interstellar and intergalactic gas-inflating lobes of glowing plasma that can stretch across hundreds of thousands of light years. These vast structures are fossil records of magnetic energy, released near the event horizon, preserved in the slow diffusion of radio waves through cosmic space. The connection between the disk and the jets is continuous. As new matter falls inward, the magnetic fields intensify, feeding the jet engine. When the inflow weakens, the jets fade, leaving behind ghostly trails of synchrotron light. This cycle repeats as the black hole consumes new material, building and extinguishing its outflows across cosmic timescales. In the immediate vicinity of the disk, magnetic reconnection continues to shape the plasma. Where field lines cross and realign, they release energy that heats the gas and contributes to the corona's X-ray brightness. These events occur in milliseconds, their combined output sustaining the luminosity of the inner accretion structure. The motion of the plasma itself remains governed by general relativity. Close to the black hole, spacetime curvature twists the trajectories of field lines and alters the direction of the jets. In a rotating system, frame dragging causes the jets to precess slightly, carving out spiraling paths that reveal the geometry of spacetime itself. Despite their scale, the jets remain exquisitely narrow, maintained by the balance between magnetic pressure pushing outward and the inertia of the flow moving forward. The power required to launch them arises not from chemical or nuclear reactions, but from the extraction of gravitational and rotational energy, pure geometry converted into motion. Observationally, the jets reveal details about the magnetic topology near the horizon. Polarization of the emitted light traces the alignment of fields, showing smooth transitions from ordered to turbulent zones. These patterns confirm that the magnetic structure remains coherent, close to the event horizon, only breaking down far from the core. At small scales, where gravity dominates the field lines, guide rather than resist motion, their curvature matching that of spacetime itself. In this environment, electric currents form naturally as plasma flows across magnetic gradients. The interaction between these currents and the fields produces radiation that fluctuates in intensity. Such variations, observed as rapid flashes or subtle flickers, provide insight into the turbulence of the near-horizon region. Despite their complexity, all these processes operate under the same physical principles. Matter moves according to curved geometry, energy follows the path of least resistance, and magnetic tension redistributes momentum across scales. From this interplay emerges a structure both elegant and efficient, capable of converting rotational motion into linear streams of radiation, extending across galaxies. The presence of these jets also stabilizes the accretion disk. By removing angular momentum and excess energy, they allow continued inflow of material without disrupting the disk's delicate balance. This self-regulating mechanism ensures that the feeding of the black hole proceeds steadily rather than explosively. Only when external events such as a burst of new infalling gas disturb the equilibrium do the jets flare violently. Then for brief intervals the luminosity of the system increases dramatically before settling again. For distant galaxies, these outbursts are among the brightest beacons in the universe. Quasars, for example, are powered by this same process, supermassive black holes feeding through accretion disks and radiating through jets that can outshine entire galaxies. Yet even in such brilliance, the source remains invisible, hidden behind layers of curved spacetime and radiant plasma. The magnetic fields, invisible themselves, are the sculptors of these cosmic forms. Without them, the disk would lose coherence, the jets would fail to form, and the surrounding space would remain dark. Instead, magnetism translates gravity's silent pressure into visible structure, linking the smallest scales near the event horizon with the largest structures in intergalactic space. From the quiet rotation of plasma within a few gravitational radii arises energy that traverses millions of light years, proof of the unity between local and cosmic physics. As the inflow continues, as magnetic tension rises and releases, the black hole remains the unmoving axis of this vast machinery. Around it, fields twist, light bends, and matter streams outward, even as other matter falls in. Both directions, descent and escape, exist side by side, shaped by the same geometry, and governed by the same laws. Here at the boundary between inflow and outflow, the universe exhibits its most efficient conversion of gravity into light. The scene is neither violent nor chaotic, but endlessly steady, sustained by balance between inward pull and outward release. The magnetic fields trace invisible paths across space, linking the hidden heart of the black hole to the glowing expanse of the galaxy beyond. At the innermost edge of visibility, light itself begins to trace the architecture of space-time. The bright ring that encircles the black hole is not a physical structure, but an optical consequence of curved geometry. It forms where photons emitted by the hot plasma of the accretion disk are bent by the intense gravity surrounding the event horizon. Some of these photons travel outward directly, others loop around the black hole once or multiple times before escaping, and many are pulled inward never to emerge. The combination of all these paths produces a luminous circular feature surrounding a central darkness, the shadow. What appears as a sharp boundary in images is in truth a smooth gradient where the probability of escape declines rapidly. The light we see has taken paths distorted through billions of kilometers of curved space-time, delayed and bent until its source and trajectory are inseparable. From a distant perspective, this ring appears steady and perfect, yet its brightness varies across the circle. On one side, where plasma in the accretion disk moves toward the observer, the ring shines more intensely. Relativistic beaming amplifies the emission, while on the far side, light from receding plasma is dimmed and redshifted. The result is an asymmetrical halo, a silent mark of motion frozen by distance and time dilation. Every photon reaching an observer's eye carries a history of struggle, a journey through extreme gravity bent and delayed each path, encoding information about the mass and spin of the black hole. The ring itself represents light that grazes the photon sphere, where gravity allows orbits of light to exist temporarily. This is the reason for its apparent sharpness. Photons from this region linger longer, creating an accumulation of brightness. The shadow, by contrast, marks the region from which no photon can escape. Its diameter corresponds to roughly 2.5 times the radius of the event horizon, enlarged by the curvature of spacetime. The interior is not dark in the ordinary sense, it is unobservable. The light that would have emerged from within never does, leaving an absence that outlines the black hole's invisible body. When the Event Horizon Telescope captured the first image of this structure, it confirmed the predictions of general relativity made more than a century earlier. The geometry of the ring matched precisely the calculations for a spinning black hole, its brightness distribution aligned with the motion of the accretion flow. Yet beyond the beauty of agreement lies a deeper simplicity. The image shows the limit of observation, the point where light surrenders to gravity. Every bright region, every shadowed contour is a map of space-time's curvature projected onto the sky. Within the bright ring, light executes impossible orbits, neither escaping nor falling, suspended momentarily in circular motion. These photons trace trajectories dictated by the Schwarzschild or Kerr metric, depending on the black hole's rotation. The difference is subtle but measurable. In a rotating system, the shadow's center shifts slightly, relative to the ring, an offset that encodes the direction of spin. Around rapidly spinning black holes, the ring itself becomes narrower on the side of rotation, stretched and compressed by frame-dragging effects that pull space-time into motion. Despite such complexity, the visual impression remains serene, a glowing circle surrounding perfect silence. To observers, the ring seems constant, but it flickers subtly as turbulent plasma in the disk emits variable light. Changes near the horizon alter brightness across the ring, creating ripples of illumination that travel at the speed of light. The fluctuations are small and transient, revealing that the structure, though stable, is alive with motion. Each fluctuation arises from matter orbiting near the innermost stable circular path, its light magnified by lensing before reaching us. The result is a cosmic mirror reflecting both gravity's geometry and matter's motion. The shadow remains fixed, but the ring shimmers faintly, marking the dynamic boundary between the observable and the hidden. In this domain, time behaves differently. To distant observers, photons appear to hover near the black hole, delayed by gravitational time dilation. Processes that unfold in seconds near the horizon may appear stretched to minutes or hours when viewed from afar. This temporal distortion contributes to the impression of stillness, the calm endurance of light trapped on the edge of oblivion. Yet for the plasma that emits it, the motion is swift orbital velocities approaching the speed of light. Space and time twist together so completely that direction loses its usual meaning. The paths of photons wrap around the black hole in spirals, looping through the warped geometry before choosing escape or capture. Each orbit they complete before release adds to the brightness of the ring. The more loops, the stronger the contribution, until further orbits vanish beyond the horizon. The black hole's shadow is therefore not the image of a surface, but the absence created by gravity's absolute claim on light. Around this boundary, the universe displays its most extreme curvature, rendered visible through the behavior of radiation. The ring is the visual boundary between knowledge and silence, between physics we can test and regions forever concealed. The image is not static in cosmic time. As the accretion flow evolves, the intensity and thickness of the ring change. Flares in the inner disk may brighten it temporarily, while long quiet periods allow it to fade. The underlying geometry, however, remains constant, defined by mass and spin alone. This constancy gives the shadow its significance. It is a direct geometric imprint of spacetime independent of the matter that illuminates it. The simplicity of its form hides a profound truth that light can reveal the shape of gravity itself. Around the bright ring, the cosmos displays its order in the midst of chaos, showing how even under conditions of unimaginable energy, physical laws remain exact. For all its strangeness, the shadow is predictable, calculable, and perfectly real. It is the visible silence of an invisible object, an image not of what exists, but of what cannot be seen. Beyond the ring lies only darkness, a region without return where light, time, and matter follow paths that no observer can trace. For now the ring stands as the last visible marker before descent, the luminous threshold of the unobservable world within. Just beyond the event horizon lies a narrow, fragile layer where light itself can orbit the black hole. This region, called the photon sphere, is defined not by matter or plasma, but by geometry alone. It represents the distance from the center, where gravity bends space-time so sharply that photons follow closed paths. Unlike the steady orbits of planets around stars, these loops are unstable. A tiny deviation in position or momentum sends light either spiraling outward toward freedom or inward toward capture. No observer could stand here, no spacecraft could remain still. The orbits belong only to light. At this distance, space and time merge into a surface of perpetual motion, where photons trace circles at nearly 300,000 kilometers per second, suspended between escape and descent. The photon sphere forms the foundation of the bright ring visible to distant telescopes, for it collects and redirects light from every direction. Photons that pass close to this region loop around the black hole several times before escaping, producing the glowing edge that outlines the shadow. The geometry of these paths is precise and elegant. In a non-rotating black hole, the photon sphere lies at 1.5 times the radius of the event horizon. In a rotating system, frame dragging causes the orbits to shift inward on one side and outward on the other, creating a slightly lopsided layer. Yet even in rotation, the principle remains the same. This is the threshold where the inward pull of gravity equals the outward trajectory of light. Inside it, all directions curve inward. Beyond it, light can still find escape routes. Within this band, the universe behaves differently. The curvature is so extreme that photons from the far side of the black hole can loop around and reach an observer's eye, allowing one to see the back of the accretion disk through the front. Each photon path becomes a record of multiple turns through warped spacetime, an imprint of geometry recorded in radiation. To the human mind, it is almost impossible to imagine light traveling in circles, returning repeatedly to the same place before departing outward. These paths create delayed echoes of events near the horizon, so that distant observers receive multiple time-staggered copies of the same flash of light. The photon sphere is therefore not only a geometric structure, but a temporal one, a place where the order of events becomes blurred by looping trajectories. Time and light intermingle, producing the illusion of stillness even amid constant motion. The photons here do not last long. Any disturbance, however small, sends them into escape or fall. Those that spiral outward fade rapidly as they stretch through curved spacetime, their wavelengths red-shifted by gravity until they merge with the background glow of the accretion disk. Those that fall inward vanish forever, absorbed by the event horizon without reflection. The balance between these two fates creates the sharp contrast between the bright ring and the black shadow. For the plasma below the photon sphere acts as both mirror and filter. Light emitted upward from the inner accretion disk may be captured and re-emitted after orbiting once or twice, adding subtle brightness to the surrounding glow. This delayed light creates a soft luminous halo around the black hole, extending slightly beyond the direct emission of the disk. Every particle of matter that approaches the photon sphere contributes to this radiance before it disappears. The temperature in the underlying disk reaches tens of millions of degrees, releasing photons at high energies. Many of these photons, unable to travel straight outward, skim the photon sphere before escaping. Their deflected paths carry with them the final visible message from matter on the brink of disappearance. For all its brilliance, this region is silent. No vibrational wave crosses it in any ordinary sense. The medium here is vacuum, yet vacuum curved beyond ordinary comprehension. Space around the photon sphere is neither flat nor straight. It is folded inward each direction, bending back upon itself. The result is a layer that behaves like a mirror made from space-time, reflecting the universe through distortion. To cross this boundary would be meaningless for anything with mass, since stable orbit is impossible. Matter that tries to remain here either falls inward or escapes outward, never pausing in equilibrium. For light, however, this is a temporary refuge, an infinite moment of turning before decision. The behavior of photons near this region has been confirmed through detailed numerical simulations of general relativity, matching the patterns observed in images of real black holes. The consistent ring size and brightness reveal the position of the photon sphere precisely as theory predicts. Its presence confirms that light follows curved paths not by influence, but by geometry itself. It is the ultimate test of Einstein's vision, a place where spacetime's curvature replaces the need for force. From the photon sphere outward, the geometry becomes more forgiving, allowing photons to escape in less twisted trajectories. But inward, the curvature increases so rapidly that even light cannot resist. The sphere marks a turning point, the last orbit of radiation before capture. If one could observe from within, the view would be extraordinary light from every direction compressed into a glowing shell, reflections of the universe folded around in a complete circle. Every star, every distant galaxy would appear multiple times distorted into arcs of colour and faint ribbons of brightness crossing the sky. Yet for an external observer, this light appears as a single narrow ring of gold encircling darkness. The simplicity of that view hides the complexity of what occurs within. The photon sphere is the final stage where light interacts with the outside universe, the last visible structure before the event horizon erases all communication. It is a surface of grace and instability, the delicate border between visibility and silence. From this layer inward, even photons cannot find escape. Their paths turn inexorably toward the singularity. Still, for a fleeting instant, light hovers here in impossible balance, its existence stretched between two fates. The ring of orbiting photons defines the true edge of the visible universe around the black hole, a shimmering boundary where gravity and light meet, where motion and stillness become indistinguishable. In that infinitesimal band, the cosmos displays one of its rarest harmonies, geometry, energy, and time coexisting at the threshold of disappearance. Beyond the photon sphere lies a narrow region where matter can still move in steady circles, before gravity finally overwhelms stability. This boundary, known as the innermost stable circular orbit, or ISCO, marks the last place where the physics of rotation remains predictable. Inside it, even the most energetic plasma cannot maintain an orbit. Any disturbance, however small, leads to a spiral inward that cannot be reversed. For a non-rotating black hole, this radius lies at 3 times the size of the event horizon. For a rapidly spinning one, it can shrink closer depending on whether matter orbits in the same direction as the spin or against it. The distinction is crucial, for rotation changes the geometry of space-time itself, dragging it into motion and altering the conditions of stability. At the ISCO, the accretion disk begins to dissolve into a plunging flow. Here the gravitational field strengthens so sharply that the difference in orbital speed between neighboring layers becomes extreme. The resulting shear stretches and heats the plasma, producing a final burst of radiation before it disappears. The gas, having radiated much of its energy already, now releases the last fraction of light as it begins its inward fall. To an outside observer, this inner edge of stability glows faintly brighter than the regions beyond a last luminous trace of matter before crossing the unseen boundary. In this region, space itself accelerates inward. Matter no longer circles freely. It is carried by the geometry of space-time toward the horizon. The spiral quickens, silently following paths calculated precisely by general relativity. The process is continuous, not abrupt. There is no wall, no shock front, only a gradual loss of equilibrium. The plasma that crosses the ISCO falls inward in less than a millisecond, a motion too fast to be seen, but not so fast that its radiation fails to escape. The photons emitted at this stage climb outward through steep gravitational gradients, losing energy and becoming redshifted. By the time they reach distant observers, their color has softened, their intensity diminished, yet their presence reveals that matter once burned brightly at the threshold of disappearance. The ISCO serves as a bridge between 2 regimes of physics: the disk of rotating plasma governed by hydrodynamics and magnetic turbulence, and the plunge region governed by pure geometry. Outside it, motion can be described in terms of forces and pressure. Inside, only space-time curvature determines behavior. The transition is smooth but absolute. Once across it, nothing can return to circular motion. The concept of stability, so fundamental in the rest of the universe, ceases to apply. The orbit's decay trajectories merge and the inflow becomes ballistic. The disk's ordered rotation gives way to free fall, a silent cascade of plasma into darkness. The region above the ISCO is illuminated by complex interactions of radiation and magnetism. Magnetic field lines anchored in the outer disk stretch across the inner zone, sometimes linking material still in orbit with plasma already falling inward. These connections transfer angular momentum outward, allowing the inflow to continue smoothly. Reconnection events in this area release sudden bursts of light, small flashes that trace the dynamics of the descent. In a sense, this narrow layer acts as the engine's exhaust, where the final conversion of the energy into radiation occurs. Beyond this, gravity claims all remaining motion. The appearance of the ISCO depends strongly on the black hole's spin. For a rapidly rotating black hole, space-time is dragged into co-rotation, allowing stable orbits to extend deeper. This difference changes not only the radius of the ISCO, but also the efficiency with which matter radiates energy. In extreme cases, nearly half of the rest mass energy of infalling matter can be converted into radiation before crossing the horizon. Such efficiency makes accreting black holes some of the brightest sources in the universe, though the light arises from a region smaller than the orbit of Mercury. Yet the luminosity hides a delicate balance. Radiation pressure here nearly equals the inward pull of gravity. A small fluctuation in density or magnetic field strength can alter the flow dramatically, leading to quasi-periodic oscillations in brightness observed by X-ray telescopes. These oscillations, measured in milliseconds, provide indirect evidence of orbital motion near the ISCO. They are the heartbeat of the accretion disk, the last rhythmic pulses before silence. For the plasma itself, there is no boundary to cross, no sudden sensation of change. The laws of physics remain continuous. A parcel of gas passes from stable orbit to free fall, seamlessly unaware of the invisible threshold it has crossed. Its temperature rises briefly as it compresses, its magnetic field lines stretch, and its radiation peaks one final time before vanishing. To an observer, this process appears frozen. Time dilation causes the infall to slow so that matter seems to hover indefinitely near the edge. The last photons it emits reach us ever more slowly redshifted until they fade from view. The disk's inner edge appears static, even though its material is long gone. This illusion defines the visual stillness of the shadow's boundary. In reality, the plasma moves swiftly, but spacetime itself conceals the motion. The ISCO is thus not only a physical transition, but a perceptual one. It marks the end of direct observation, where the difference between appearance and reality becomes governed entirely by relativity. Within this radius, space curves inward faster than any signal can travel outward. The plunge begins invisible but inevitable. Yet even here, gravity's precision persists. The equations of general relativity describe every detail: how energy dissipates, how angular momentum is transported, how light bends and fades. There is no chaos, only order too complex for the senses to follow. The ISCO stands as the final limit of motion that remains comprehensible. Beyond it lies simplicity again, complete surrender to geometry. All that enters continues inward on paths that cannot be seen, carrying with it the memory of light, the imprint of magnetic fields, and the final whisper of energy released before silence. It is the threshold between the known and the unknowable, a ring of invisible motion marking the last stand of stable matter. The journey that began among stars now reaches its irreversible descent, and every photon escaping from this edge carries the same story: that order persists even in collapse, that light can trace the edge of eternity before fading into the dark. At the very boundary of the black hole lies the event horizon, the invisible surface that divides the observable universe from the unobservable. It is not a wall or a membrane, nor does it exert physical resistance. It is a threshold defined entirely by geometry, the point at which the escape velocity equals the speed of light. Beyond it all, trajectories curve inward, and no signal, not even light itself, can return to the outside world. From afar, this region appears as the dark center of the shadow, motionless and absolute. Yet in reality it is dynamic, continuously fed by matter and radiation that approach and vanish silently. For an observer far from the black hole, the event horizon represents the limit of time as much as of space. As an object falls toward it, the light it emits is stretched by gravity, its wavelength growing longer, its brightness fading until it disappears entirely. To the distant eye, the fall never completes. Each moment of descent slows, each pulse of radiation takes longer to arrive, frozen asymptotically at the edge. The infalling matter seems suspended on the threshold, its motion halted by time dilation. Yet in its own frame of reference, the fall continues smoothly. The crossing of the horizon is unremarkable, free of any physical shock. Local space-time remains continuous. The laws of physics do not break. To the falling particle, it feels like any other region of vacuum, though its future path is already sealed. The distinction between these two perspectives, one external, one internal, is one of the most profound consequences of relativity. To the distant observer, the horizon is a permanent boundary. To the falling traveller, it is a moment that passes without resistance. Both views are correct within their own frames, coexisting as separate truths shaped by the geometry of space-time. The event horizon itself is defined by null trajectories, paths of light, that neither escape nor descend. It is the surface traced by photons that remain forever balanced on the edge, orbiting the black hole at the exact angle where escape and capture are indistinguishable. In a rotating black hole, this surface is not spherical but ablate, flattened by spin. Its radius changes depending on direction, smaller at the poles and larger at the equator. Rotation drags space-time around with it, tilting the horizon and causing the surrounding light paths to twist. Despite this complexity, the horizon remains a perfect one-way boundary, a region from which no signal can propagate outward. In physical terms, the event horizon is defined not by material composition, but by causal structure, the separation between events that can influence the outside universe and those that cannot. Inside, all paths lead inexorably to the center. Outside, motion and communication remain possible between the two time and space exchange roles. The mathematics describing this region reveals a subtle symmetry. The same equations that govern the orbits of stars also govern the curvature of time itself near the horizon. In the steady accretion flow, the event horizon is continuously fed by plasma spiraling inward. To a distant observer, this matter appears to pile up just outside, forming a glowing shell that never fades completely. The last photons emitted before crossing are stretched into longer wavelengths, blending into faint radio waves that persist for ages. In reality, the material has long since crossed the boundary, leaving only this spectral ghost behind. This illusion gives rise to the impression of permanence, as though the black hole were frozen in time, its surface glowing faintly from the arrested descent of matter. Yet to the universe at large, the horizon is an active participant in cosmic energy exchange. It absorbs all that reaches it, radiation particles, even neutrinos, transforming their mass and energy into the growth of the black hole itself. Every act of infall increases the curvature of space-time, deepening the gravitational well. The horizon expands slightly with each addition, its circumference growing in proportion to the increase in total mass. This growth is one of the few measurable changes a black hole undergoes, for everything else beyond it is hidden from observation. At quantum scales, the event horizon may not be entirely silent. According to theoretical predictions, it emits faint thermal radiation, a phenomenon known as Hawking radiation, produced by quantum fluctuations at the boundary. Though immeasurably weak for astrophysical black holes, this process implies that even horizons are not eternal. Over unimaginable timescales, they may shrink as they radiate energy back into space. For now, however, the effect remains far beyond detection, overshadowed by the immense inflow of ordinary matter. The surface of no return endures as one of nature's most perfect absorbers. No reflection, no transmission, no echo escapes it. All information that reaches it becomes part of the black hole's hidden interior, its imprint encoded only in the horizon's surface area and spin. In the geometry of relativity, the event horizon represents entropy in its purest form, a measure of information concealed from the external universe. The black hole's entropy, proportional to the area of its horizon, defines a bridge between gravity thermodynamics and quantum mechanics, suggesting that space-time itself may carry microscopic structure. Though this remains theory, the implications reach beyond astrophysics, touching the foundations of physics itself. Observationally, the event horizon reveals itself only indirectly through the absence of light. The glow of the accretion disk stops abruptly at its edge, the transition sharp yet smooth, as if the universe had been cut off mid-sentence. In radio images, this boundary defines the dark center of the ring, a void that no telescope can penetrate. It is the silence behind the brilliance, the perfect absorber at the heart of the cosmos. Yet the horizon is not an endpoint in the structure of reality. It is a coordinate surface, a feature of geometry that marks where causal connection ends for the outside world. Beyond it, space-time continues curvature, deepening toward the center. The horizon merely hides what lies beneath, preserving the symmetry between inner and outer worlds by forbidding the exchange of light. To stand outside it is to see the universe distorted but intact. To cross it, in theory, is to enter a region where the future points inward and all motion converges toward a single destination. The event horizon is the most absolute boundary known to science, not of matter, but of knowledge itself. Around a rotating black hole, space-time itself does not remain still. The immense angular momentum of the singularity twists the geometry of the surrounding region, forcing everything nearby into motion. This domain, known as the ergosphere, extends just outside the event horizon and is bounded on the outside by a surface called the static limit. Inside the static limit, no object, not even light, can remain stationary with respect to distant stars. Space and time are dragged around the black hole as though caught in a slow whirlpool of geometry. It is not a mechanical rotation, but a curvature of space-time itself, where the meaning of direction becomes inseparable from motion. The phenomenon is called frame dragging. Within this region, all paths curve in the direction of the black hole's spin, and even light emitted opposite to the rotation is carried along. To remain fixed would require moving backward faster than light, relative to the local space-time an impossibility. Thus, every particle, photon and field line is compelled to rotate with the black hole tracing arcs, determined by the geometry of the Kerr metric. The ergosphere is shaped like a flattened sphere touching the event horizon at the poles and bulging outward at the equator. Its size depends on the rate of spin. The faster the rotation, the larger the distortion. In this swirling domain, energy can be extracted from the black hole's rotation, a process predicted by physics but rarely witnessed directly. If a particle falls into the ergosphere and splits into two, one fragment can escape with more energy than the original possessed, while the other falls inward with negative energy relative to infinity. The loss of this negative energy reduces the black hole's spin, slightly converting rotational energy into observable radiation. This theoretical process, known as the Penrose mechanism, demonstrates that even the most absolute gravitational trap can share part of its energy with the universe. Though the efficiency is low, it illustrates the profound coupling between motion and geometry. The same principle operates in magnetically driven jets. The twisting of magnetic field lines in the ergosphere channels rotational energy outward, sustaining the narrow beams that emerge from the poles. In this way, the black hole's spin becomes a source of cosmic power. Frame dragging also affects the paths of matter in the accretion disk. Orbits closer to the black hole precess in the direction of spin, causing the disk to warp slightly. The inner region may tilt until its plane aligns with the black hole's equatorial plane, a phenomenon known as the Bardeen-Peterson effect. This alignment shapes the direction of jets and determines the symmetry of emission. Observational evidence for these effects comes from subtle shifts in light polarization and from the orientation of jet structures in active galaxies. They confirm that the geometry around spinning black holes behaves exactly as general relativity predicts, not as an abstract curvature but as a physically rotating fabric of space-time. Inside the ergosphere, time itself acquires motion. every attempt to remain still results in rotation. An observer here would find that even without thrust, they revolve around the black hole simply by existing. The rotation of space-time means that inertial frames, the natural states of rest defined by relativity, are themselves in motion. In this sense, frame dragging redefines what it means to move or to be at rest. It is the ultimate demonstration that space and time are not backgrounds but participants in dynamics. The degree of dragging increases toward the horizon. At the boundary, the motion of spacetime matches the speed of light, merging seamlessly with the event horizon's one-way flow. The ergosphere therefore acts as a transitional zone between regions of ordinary motion and those where geometry dictates every path. Within it, the distinction between energy and rotation blurs for kinetic and gravitational energy exchange continuously through curved spacetime. The black hole's spin also influences how light escapes from the region. Photons emitted against the rotation lose energy as they climb outward, while those emitted with the rotation gain it, producing a characteristic asymmetry in observed brightness. This effect contributes to the ring's uneven glow, one side brighter and bluer than the other. The light's polarization further reveals the presence of twisted magnetic fields aligned with the spinning geometry. The ergosphere is thus both an engine and a mirror, a region where the invisible motion of spacetime leaves visible imprints on radiation. The structure of the ergosphere is mathematically elegant but physically extreme. At any instant, the metric defining distances and times is distorted, and all quantities that describe rotation intertwine. Angular momentum energy and time behave as components of one continuous entity. The deeper one moves, the more this coupling intensifies. At the outer edge of the ergosphere, the effect is gentle, merely shifting orbital frequencies. Near the horizon, it becomes absolute, sweeping all motion into alignment with the black hole's spin. The interplay between frame dragging and magnetic fields may also help stabilize the accretion disk. By transferring angular momentum outward, the rotation of spacetime itself supports the continuous inflow of matter. The energy extracted through these processes contributes to the radiation seen from quasars and X-ray binaries, connecting microscopic curvature to cosmic-scale luminosity. From a distant view, the ergosphere cannot be seen directly. Its presence is inferred from the behavior of light and matter, from the precession of orbits, and from the polarization of emission. It is a region defined not by brightness, but by motion. If one could visualize it, it would appear as a translucent shell surrounding the black hole, slowly spinning with invisible grace. Within it, the flow of time becomes circular, looping endlessly around the center. To exist inside the ergosphere is to be carried along by the rotation of space-time itself, unable to resist yet still free to escape outward along the right trajectory. Beyond it, ordinary geometry resumes, within the direction of all future's curves around the black hole's axis. The ergosphere embodies relativity's most extraordinary prediction that rotation can twist the fabric of existence, and that even emptiness can spin. It is the cosmic boundary where gravity becomes motion, and motion becomes gravity, a silent whirlpool in which space and time themselves revolve around the darkness they conceal. At the threshold of the event horizon, the distinction between outside and inside becomes one of perspective. To a distant observer, the infalling plasma never quite crosses. It slows, fades, and disappears asymptotically. But from the viewpoint of the matter itself, the crossing occurs swiftly, without resistance or perceptible boundary. Space and time stretch together, continuous and smooth, offering no sign that a line has been passed. The plasma continues its descent, carried inward by geometry, oblivious to the fact that its light will never escape. There is no surface, no barrier, no shock wave. The equations of relativity ensure that locally nothing unusual occurs. Gravity does not crush instantly. It simply curves the path of every object toward the center. Inside the horizon, all directions now point inward. Motion through space becomes motion through time, and the center becomes not a place in space, but a moment in the future that cannot be avoided. For the falling particle, the passage is uneventful. It experiences the same local laws of physics as before, obeying the same relationships of energy and momentum. But the structure of space-time around it changes fundamentally. The coordinates that once described distance now describe duration. The inward direction becomes equivalent to the flow of time itself. Once the horizon is crossed, return becomes as impossible as moving backward through time. To the outside universe, the object's story ends here. Its remaining signals are stretched endlessly, its information sealed behind the boundary. Yet for the object, existence continues now enclosed within the deeper curvature of space-time. The crossing is therefore both an ending and a continuation, a moment where perspective divides reality into two irreconcilable halves. The falling matter moves through a region where the metric changes sign. Distances and intervals reverse their meaning, and causal order becomes fixed toward the center. Still locally, the rules of motion remain familiar. Objects follow geodesics, freefall paths determined by gravity alone. They do not feel the curvature, only its consequences. The view of the universe above shifts as light from the outside bends inward, wrapping around in distorted arcs. The sky of the external cosmos contracts into a bright ring, behind compressed by gravitational lensing, while ahead lies only darkness. Photons entering the horizon follow the same fate as matter. Their trajectories converge toward the singularity. The infalling plasma continues to emit light, but that light never escapes. To distant eyes it freezes and fades. To itself it streams forward, merging with the gravitational field that guides it. Time for the infalling matter proceeds normally, but its duration before reaching the singularity is finite. Within seconds or minutes, depending on the black hole's mass, it will reach regions where density and curvature approach infinity. Yet this approach too is smooth in experience, for gravity acts uniformly on every part of an object, leaving no differential stress until the final moments. Larger black holes stretch these moments, spreading the descent across longer intervals, while smaller ones compress them into instants. In every case, the physics remains continuous. The passage through the horizon is invisible to any local observer. Instruments measuring acceleration, radiation, or pressure would detect no sudden spike. Only the surrounding geometry betrays the change, ensuring that all possible paths now terminate inward. The horizon behaves like a river whose flow accelerates faster than light, carrying everything downstream. Space itself moves inward, faster than any particle can resist, and no propulsion could reverse direction. Even light emitted directly outward is swept along its forward motion, counteracted by the inward drag of space-time. The analogy is imperfect, but useful in the language of relativity. Space-time flow replaces force. The traveller does not feel pulled. They simply follow the current of geometry. If one could look outward after crossing, the view would appear frozen. The external universe would seem to slow its clocks running faster, relative to the local one, until they appear to halt altogether. Stars would blur into a single faint glow as their light redshifts to invisibility. The black hole's shadow would close behind like an illusion, not by motion, but by loss of connection. Communication with the outside ends instantly at the horizon, for signals emitted outward never cross back. The traveller's future becomes entirely interior, their link to the rest of the cosmos severed. Yet inside the geometry remains orderly. Space-time continues to curve smoothly toward the core described precisely by the equations of Einstein's field. The curvature strengthens, tidal forces begin to rise, but for now, they remain small compared to the immense scale of the black hole. Only near the singularity do these forces grow catastrophic. In supermassive black holes, the crossing is surprisingly gentle. The gradients of gravity are so vast that no object, even a spacecraft, would be torn apart at the horizon. The interior is silent, featureless, and dark. No light reflects, no signal propagates. The sense of direction is lost, for all directions lead to the same future. Motion continues automatically without the need for propulsion or will. Every atom of the infalling matter shares the same fate carried along geodesics that end at the same central point. The transition from observation to isolation is total. The outside universe can no longer witness what happens within, and those inside cannot witness what lies beyond. The event horizon is not simply a barrier in space, it is a one-way membrane in causality. It separates what can be known from what cannot. The crossing thus represents a change in the very structure of information. From the outside, all that remains of the infalling matter is its contribution to mass charge and spin the conserved quantities that define the black hole. Everything else, every trace of detail, becomes part of the horizon's entropy, encoded on its surface as a measure of lost information. Inside, the descent continues smoothly toward the central region, where curvature and time merge. The falling matter becomes part of the geometry itself, indistinguishable from the fabric of space-time it now inhabits. In this realm, there is no longer a distinction between motion and existence. Everything is motion. Everything is descent. The journey that began in the calm rotation of the galaxy now passes the point of no return, entering a region where light, space, and time lose their independence. The crossing is quiet, unnoticed, irreversible, the final threshold between the visible universe and the unseen domain that lies beneath. Beyond the event horizon, the familiar structure of reality collapses into geometry alone. Space and time no longer behave as separate entities. They trade roles entwined within the curvature of the black hole's interior. Every possible trajectory now points toward the center, not by force, but by the definition of space-time itself. Motion is no longer a choice, it is destiny. The interior is not a place that can be entered and then left. It is a region of space-time where all future moments lead inevitably toward a single endpoint, the singularity. No light signal or event within can influence the outside universe, for causal paths terminate inward. The interior remains hidden not by obscurity but by the structure of the cosmos. What happens here unfolds beyond all horizons of communication. Within this region, the equations of general relativity still apply, but their consequences are unfamiliar. Distances contract, timescales distort, and the geometry accelerates inward. The direction that once measured distance from the center now measures time until arrival at the singularity. To an infalling observer, there is no sensation of confinement or end. The fall continues smoothly, and nothing indicates a boundary crossed or a path shortened. The laws of physics persist, but the meaning of those laws changes. Every object, every photon, every grain of matter that crosses the horizon follows its own geodesic toward the center, converging silently with all others. No signal between them can overtake the flow of space-time itself. Communication becomes increasingly impossible. The deeper they fall, the closer the future narrows to a single point. If one could visualize this interior, it would not resemble darkness in a conventional sense. It would be absence, the elimination of all reference points that define perspective. The universe outside would appear as a shrinking halo of light fading quickly, As gravitational redshift drains its color and energy, the horizon closes above not like a door but like a vanishing coordinate erased from existence. Within moments only a dim afterglow remains, then nothing but silence. Matter continues inward through curved space which now funnels all motion toward the singular line or ring at the center, depending on the black hole's spin. In a rotating black hole, the interior may contain regions of frame dragging so intense that space itself whirls faster than light around the axis. This twisting geometry leads to theoretical zones where causality breaks down, though such areas remain purely mathematical. In physical reality, all paths still end at the singularity, where the known laws of physics lose meaning. The experience of falling inward through this geometry would be paradoxical. Locally everything feels normal, no acceleration, no sensation of speed. Yet external events appear distorted, frozen at the edge of sight. Clocks, if they could survive, would record only a finite interval between crossing the horizon and reaching the singularity. In a black hole of stellar mass, that duration would be measured in seconds. In a supermassive black hole, it could last hours. But for the outside universe, no such passage exists. The traveller is frozen at the horizon forever. Both descriptions remain true within their own frames. This duality of perspective, smooth continuation inside, eternal stasis outside, is one of the most striking features of relativity. It demonstrates that time itself is relative to geometry, and that the end of one observer's journey may never occur in another's universe. The matter within the black hole follows the same path of inevitability. Layers of plasma dust and radiation collapse inward, compressed beyond atomic scales. The density increases without limit, and the curvature of spacetime steepens until the equations describing it diverge. The singularity that forms at the center is not a physical object but a region where mathematics fails, where gravity becomes infinite, and spacetime ceases to have measurable shape. In theory, all the mass and energy of the black hole reside there, concentrated into zero volume. The concept challenges comprehension, for infinity is not a value but a breakdown of description. What exists at that point remains unknown. Infalling matter never reaches the singularity in the same external time that the universe measures. Each step inward corresponds to an increasingly smaller fraction of cosmic time, asymptotically approaching an instant that never completes. To the infaler, however, the end arrives swiftly. The curvature increases exponentially, and tidal forces differences in gravitational pull between near and far sides of the body begin to stretch and compress. For small black holes, this process called spaghettification occurs long before the center. For supermassive ones, it happens only in the final moments. In either case, no structure can survive. The distinction between object and space dissolves. Everything becomes geometry. Within this collapsing framework, energy and information continue to exist, though their organization becomes impossible to define. Quantum theory suggests that information cannot be destroyed, implying that it must somehow remain encoded in the black hole structure or radiation. But within classical relativity, all such details vanish into the singularity. The field equations no longer yield solutions beyond that point. Thus, the black hole's interior stands as the limit of physical knowledge. It is not a void, but a concentration of existence so dense that distinction itself disappears. Time, space, matter, and energy merge into a single indivisible continuum, headed toward mathematical infinity. If one could pause within this interior, which is impossible but imaginable, one would see no landmarks, no direction, no distance. The universe outside would no longer be visible. Even the concept of outside would lose meaning. Every possible path forward points to the same destination. The singularity is not a point in space, but an inevitable event in time, the future of everything that crosses the horizon. For each black hole, this convergence is absolute. The entire interior is a funnel of fate, an unobservable conclusion to the visible drama of cosmic accretion and light. Yet the equations describing it remain consistent and elegant. The Schwarzschild and Kerr solutions of general relativity define every curvature, every interval, every light path until the singularity itself is reached. Within their scope, nothing is random. The interior is deterministic, governed by mathematics of extraordinary simplicity. Only at the final limit does comprehension fail, not because nature ceases to function, but because human theory cannot extend further. What lies beyond the singularity, whether it is destruction, continuation, or transformation, is not known. The laws of spacetime, as we understand them, end here. Inside the event horizon, existence becomes a continuous fall into the future. Each step inward compresses time, space, and energy into a single, seamless descent. There is no light, no communication, no return. And yet, in the quiet perfection of its geometry, the black hole remains a complete system, self-contained, mathematically coherent and eternal from the outside view. The crossing of the horizon was the last visible moment. All that follows occurs within a silence so absolute that it erases not only sound and light, but the very distinction between movement and stillness. Deeper within the black hole's interior, the curvature of spacetime intensifies beyond all measure. Every trajectory now funnels toward the singularity, the theoretical core where density and gravitational force become infinite. The descent that began gently in the outer regions has become unstoppable, not by acceleration but by geometry itself. Time and space have exchanged roles completely. Moving inward is no longer a direction in space, but a progression through time. Every future moment for all objects inside leads to the same destination, the central point of convergence. No physical process can alter this outcome, for the structure of space-time allows no other path. The environment becomes increasingly hostile to the familiar notions of distance, mass, or energy. The gradients of gravity grow so steep that even the smallest separation between 2 points yields enormous differences in force. These tidal effects stretch matter along the inward axis and compress it sideways. To any object, these forces would rise from imperceptible to overwhelming in a fraction of a second. Molecular bonds would fail, atoms would deform, and subatomic particles would be torn from one another. The fabric of matter disintegrates into pure energy, and even that energy becomes indistinguishable from the geometry that contains it. In falling radiation, having been trapped and redirected countless times, adds to the mass energy of the system, feeding the singularity silently. The process is absolute. There are no rebounds, no oscillations, only the steady inward convergence of all things. Yet even here the mathematics of relativity remains precise. The interior obeys the same field equations that govern stars and galaxies, only pushed to their extreme limits. These equations predict that as curvature increases, proper time to the singularity decreases. The infalling observer experiences the approach as an inevitable sequence ending in a finite interval. The singularity lies ahead in time, not space. It cannot be seen or approached by avoidance, for all future trajectories end there. For each moment of descent, space narrows and time shortens until the two merge into a single termination point. For an external observer, none of this unfolds. The horizon remains frozen and the fall appears incomplete. Inside it is over swiftly the end of all possible events contained in moments. In a rotating black hole, the structure is more complex. The singularity is not a point, but a ring, an infinitesimally thin loop of infinite density surrounded by regions of extreme curvature. The geometry here allows for peculiar mathematical solutions, potential tunnels, and alternate regions of spacetime known as extensions. But these remain hypothetical. In reality, quantum effects and instabilities would almost certainly erase such passageways, leaving only collapse. The equations suggest possibilities beyond known physics, yet observation is forever barred. No experiment can probe this domain. What exists here is speculation constrained by mathematics and the limits of understanding. As the singularity is approached, energy densities surpass all known scales. The temperature, though meaningless in classical terms, would exceed any physical measure, as kinetic motion becomes dominated by space-time curvature rather than by thermal agitation. The distinction between heat and motion vanishes. All particles, now indistinguishable from one another, follow geodesics converging toward the same mathematical endpoint. The concept of direction loses meaning. Only convergence remains. The closer to the singularity, the faster time collapses. Each infinitesimal moment brings exponentially greater curvature until the entire past, present, and future of the interior compress into a single surface of infinite density. The singularity itself, as predicted by general relativity, is not a thing, but the breakdown of the equations that describe reality. It is where the mathematics stops, where quantities such as density, pressure, and curvature diverge to infinity. At that limit, space-time ceases to be continuous. The physical meaning of distance, duration, and even causality dissolves. The geometry becomes undefined, and with it the laws of physics as we know them. The singularity is therefore both an end and a beginning, a limit beyond which prediction fails. It represents the frontier of knowledge, the point where classical theory gives way to mystery. Physicists expect that a deeper framework, perhaps involving quantum gravity, would resolve the infinities and replace the singularity with a finite though extreme state of matter and energy. Until such a theory exists, the singularity remains an unavoidable consequence of general relativity and the ultimate boundary of understanding. From a conceptual standpoint, the singularity marks the compression of all history into one instant. Every event that ever crossed the horizon becomes part of it, not as individual memories, but as a single contribution to curvature. Information, mass, and energy cease to exist as separate quantities. They become attributes of space-time itself. Some theories suggest that information might not be destroyed, but encoded at the horizon, preserved holographically. Yet inside, where no signal escapes, such information has no physical manifestation. The singularity absorbs without trace, erasing all distinctions, while preserving total conservation of mass energy in abstract form. The physical experience of nearing the singularity, if one could remain conscious, would be dominated by tidal stretching. The differences in gravitational pull across even atomic scales become infinite, aligning everything into long, narrow filaments that continue to thin until they merge into the geometry. For supermassive black holes, this disintegration occurs near the very end of the journey. For smaller ones, it happens almost immediately upon entry. In either case, there is no survival, no observation of the final moment. The equations describing proper time show that the end arrives in finite duration for any infalling observer, but from outside the horizon it never occurs. The fall is eternal to the cosmos and instantaneous to the traveller. The singularity thus stands as the deepest paradox of gravity, a point predicted by precise mathematics, yet unreachable by experiment and entity, that ends space and time while preserving their total energy. It embodies the limits of comprehension. Beyond it, no geometry can be drawn, no clock can tick, no equation can describe. And yet in its presence the universe maintains consistency. The same laws that govern gentle orbits and falling stones lead inevitably to this extreme. The singularity is not an exception to nature, but its most complete expression of gravitational order. All curvature leads here, all trajectories converge here, all time ends here. The interior of the black hole, though invisible, remains connected to the universe through its effects. The mass that has fallen in continues to shape the curvature outside, defining the motion of stars, the paths of light, and the dance of galaxies. The singularity's silence becomes the galaxy's structure. The energy trapped within sustains the gravity that holds entire systems together. Thus, the most extreme concentration of mass produces not chaos, but stability on cosmic scales. The end of matter inside the black hole gives shape to the order beyond it. The singularity is the unseen foundation of the galaxy's architecture, the ultimate convergence of space and time into one absolute eternal point. At the final limit of descent lies the black hole's most elusive feature, the unknown core. Here theory falters and observation is impossible. The equations of general relativity predict infinite curvature and density, yet infinity is not a physical quantity, but a signal that understanding has reached its boundary. The singularity, as it is called, is not a structure within space. It is the end of space itself. Inside this region, all paths converge, all timelines collapse, and the familiar framework of cause and effect dissolves. No event within can be seen described or measured from beyond the horizon. The universe continues outside, oblivious to what unfolds here, while within all that once had form and motion is drawn into a state without dimension. The singularity is the place where physical theory stops. General relativity, which so precisely describes the motion of planets, the bending of light, and the structure of galaxies, predicts its own breakdown here. The infinities that arise in the equations suggest that another framework, one combining quantum mechanics with gravity, must exist to replace them. Such a theory, still incomplete, would describe how space and time behave when compressed, beyond the Planck scale where quantum fluctuations dominate. Until it is found, the nature of the core remains unresolvable. Some models propose that the singularity could be replaced by a finite but extraordinarily dense state, a quantum remnant where the energy of space-time is confined but not destroyed. Others suggest that the laws of physics near the singularity might create bridges to new regions of space-time, hypothetical constructs known as wormholes. These possibilities remain mathematical exercises, not physical evidence. What can be stated with certainty is that the singularity, if it exists, is hidden forever from the rest of the universe, concealed behind the event horizon's eternal silence. To the matter that has fallen inward, the singularity is inevitable. Every path, regardless of initial direction, terminates here. The concept of where becomes meaningless, for there is no space left in which position could be defined. The mass and energy that have entered contribute to the curvature, increasing the gravitational field that continues to shape the galaxy beyond. From the outside, this influence is complete. The black hole's mass, spin and charge define everything that can be known about it. No trace of the objects that once fell inside remains, no record of composition, structure or history. This simplicity is remarkable. The most complex collapse in the universe reduces to three quantities, a principle known as the no-hair theorem. A star, a planet or a cloud of gas all become identical once swallowed their individuality, erased their details, compressed into a single gravitational signature. The singularity is thus not a remnant of the past, but an active process of simplification. It is the ultimate reduction of matter into geometry. Yet the simplicity of its external description contrasts with the mystery within. Quantum theory, which forbids the destruction of information, seems incompatible with the idea that details are lost forever. This conflict, known as the information paradox, has driven decades of investigation. One resolution suggests that information is not destroyed, but stored on the event horizon encoded in microscopic fluctuations of spacetime itself. Another proposes that the Hawking radiation emitted from black holes over vast timescales carries away this information, subtly preserving the universe's total record. Each idea remains partial, a glimpse of an unfinished synthesis between gravity and quantum mechanics. Whatever the answer, the core of the black hole holds it hidden from view, yet central to the structure of reality. The physical state of the singularity, if such a state can be defined, cannot be visualized. All attempts to imagine it fail because imagination depends on geometry, and geometry ceases here. There is no inside, no outside, no direction of movement. The singularity is the end of measurement and the collapse of scale. Time, which once flowed smoothly, folds into a point. The past, present, and future become indistinguishable, compressed into an instant of infinite curvature. The entire history of the matter that formed the black hole, every photon that ever crossed the horizon, converges into this single termination. Yet from outside, the black hole endures as a stable, unchanging feature of the cosmos, its external geometry smooth and eternal. The contradiction between the chaos within and the serenity without defines the black hole's dual nature, a paradox of completeness and concealment. In theoretical models, space-time might not end absolutely. Some versions of quantum gravity propose that at scales beyond current understanding, the curvature could rebound, forming a new region of expansion. If true, the singularity could act as the seed of another universe invisible to ours. In such a picture, black holes might serve as cosmic wombs, giving birth to new domains of space-time disconnected from their origins. These concepts remain speculative without evidence or means of verification. Still, they illustrate how the unknown core of a black hole forces physics to its most profound questions. Is space-time finite or recursive? Is information preserved eternally, or can it vanish beyond recovery? Can the universe contain its own origins within its hidden depths? The answers lie beyond observation, locked behind the veil of geometry. What endures beyond the singularity is not known, but its presence shapes everything around it. The curvature it creates extends outward indefinitely, governing the motion of stars, the evolution of galaxies, and the distribution of light across the cosmos. The singularity's silence defines the universe's architecture, connecting the smaller scales of collapse with the larger structures of order. It is both the consequence of gravity and its source, the invisible counterpart to all the brightness of the stars. In its depth lies the universe's ultimate symmetry, every act of creation balanced by an act of absorption, every expansion matched by collapse. The black hole's heart is the mirror of the cosmos, absolute darkness reflecting absolute order. And yet, despite the finality it represents, the singularity is not destruction. It is transformation. Matter, energy, and even the concept of time themselves do not cease. They are redefined in terms of geometry. The unknown core is less an end than a horizon of understanding, a point where human theory meets the vastness of nature's design. In the quiet at the center of the black hole, the universe hides the mechanism of its own continuity. Whether it is infinite, cyclic, or terminal remains unseen. All that can be said is that the journey inward concludes not in violence, but in stillness, the stillness of perfect gravity, perfect symmetry, and perfect mystery.